Okay. Oh, you have a nice background. I like it very much. Hello, Sarah.
Hello, Professor. Good morning. Lucia.
Hi.
So I don't know if more people will join, but since it is recorded, it will be okay. So I will try my best for finishing in time. I know that you need to be at other place, so it shouldn't be more than 1 hour. There are two things that I would like to ask everyone who takes the class. One is to make a selection what you would like to present. So the presentation itself is not optional, is mandatory, but the subject is free. You select what you like. Good morning. Morning. I see you. Good morning, Boston.
Morning.
So there probably the most important thing is to perform signing up, and I'll share the screen and watch and show how to fill this form. So the date of presentation is open. If someone wants to do it earlier or later, I can take it into account. Tentatively, we should plan on next Friday or maybe Tuesday after the weekend. But since it is quite easy, maybe next Friday in a week from now is better. But I'll hear your voices. When I'll start sharing screen and showing slides, we'll do it together. Another thing. I would like to offer you a little informal homework. I even didn't type it and didn't formulate it, but at the end of today's meeting, we will get a new concept, new for the course. I'm more than confident that it is not new for you and not new for me, but the name of the concept is potential energy, right? You all know what it is. And in terms of the course, people call it potential energy surfaces because it often depends on several degrees of freedom because there are so many ions. And if there are at least 2 degrees of freedom, it's not a curve as we do in basic physics, but at least 2-dimensional potential, like 2 independent degrees of freedom and 1 potential. So the informal homework that I would like to ask you to do during the weekend, and, I don't have intentions to assign homeworks over the weekend. I'll try to avoid it in the future. But you may want to prepare one PowerPoint slide. Good morning, Stephen. Nice seeing you connected. One PowerPoint slide with summary of your understanding, with your personal definition of what is potential energy surface. And you're welcome to use materials from the lecture or from Wikipedia or from other sources. So it's better to be more visual, and like some of you have experience of serving as teaching assistants for undergraduates. So think not of telling me what it is, but telling someone from undergraduate classes, just one slide of definition. Okay, and before I start sharing slides, let me make a quick overview what to expect. So, in some sense, I'm not going to tell anything new today. In principle, I'm going to wrap up the big intellectual leap forward that we did on Tuesday. So I will summarize our description of Born-Oppenheimer approximation. And if you were glancing through slides, as always, they're ugly because I do not have sense of beautiful slides, and they're long. But I'll skip most of them and focus only on important things. So our goal was to separate electronic and nuclear degrees of freedom, and basically we are almost there. I just need to repeat main steps and summarize the output to highlight what are the independent equations for electrons and nuclei. And as soon as we go over this material, as we set up definitions of the bad terms in molecular Schrödinger equation, bad not in our relation to them, but in mathematical sense, uncomfortable terms. So the terms that are being dropped in the Born-Oppenheimer approximation, we'll give them names, we'll give them symbol to define, and then we'll forget about them for most of our life. And then I will try to look on both equations for electronic and nuclear degrees of freedom and look how electronic degrees of freedom still have some influence on nuclear degrees of freedom and help to redefine the interatomic forces or potential of interaction between atoms, taking into account the electronic effects. So I never was trying to explain it to unprofessional audience, so I'm always speaking to intellectual elite as you are. But I'll maybe try to set it in a simple way before we go to the slides. All nuclei are positive, and if we put a shield between two nuclei, if we put a negative charge between them, it may compensate their action on each other on one hand and make the interactions weaker. On the other hand, there is an opportunity if there is a like strong electronic cloud, there is a shield between them, both nuclei will attract to it and stay closer. So they repel less and attract more due to interaction with electrons. And therefore, nuclei to nuclei interaction depends on electronic degrees of freedom, and it defines internuclear forces. It defines potential that nuclei experience if the position are changed. And this is basically potential energy surface. Why we need it? So in some research groups that you represent, the main focus is not on electronic structure, but only on the nuclear configurations. So people do molecular mechanics for geometry optimization or molecular dynamics to see how positions of ions change in time and stop there, because it also gives a lot of valuable and interesting information. So if we do not want to look beyond this point, we still need to understand how the interaction between nuclei, where it comes from. And in this sense, today's lecture can be useful, even if actual electronic states is not your primary interest. Okay, so feel free to stop me to ask any questions anytime, especially when I open slides and start going over them like crazy. I may not see your faces, so do not hesitate to just loudly speak into microphone and stop. Okay. I need to share screen. and presentation, sign up. So before we go forward, I invite everyone to watch this link, and I believe I did send it and made everyone privileged as an editor, but just in case, let me send it into the chat line. Chat. So the amount of subjects is larger than amount of class attendees, but they are quite simple, and I suggest that everyone takes two or even three, and maybe if there is a conflict, if several people are trying to um, sign up for the same subject, then I will try to resolve conflict and convince what would be the best arrangement for interest of everyone. So, for example, if I want to present on HyperCam, I can just type my name here. So I already see. So it hides your names. It shows like anonymous characters, but you can click onto right spot and type your name. I will try to return to this table at the end of the class and see how it goes with filling, with putting your votes. But please practice the democracy. I think it will be much better compared to if I assign people to subjects. So you select what you prefer, and this is what we did during the last lab. So I think everyone should be happy about it. Let me check who has an account on CCast. Okay, 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 good. Then you can also compete who wants to present this basics. I'm skipping it in the labs, but those who have, one of those who has account on CCast can give a little masterclass explaining others which site to go, how to log in, and basically make 3 minutes introduction onto this facility. Okay, so I will return to this page at the end and hope you will and hope to see some votes. And now let me bring the slides up. So about 80% of these slides, maybe 70, is already what we did. So I'm going to go very quickly from beginning to about the last yellow page to here, maybe as a reminder, and new things will start after. Um, okay, so it is approximately where we are in the class. Here are examples of sign up list from previous years, and if you have some friends in this list, you may consult with them which subjects are reasonable. Like some of you are acquainted with Amir. You see, he was presenting Babel, and here I just disclose my plans for next homework that will be next week. So we started describing molecules as set of, and now you can lean back and relax. I will give you a sign when there will be something important in you. So we describe molecules as set of positive nucleus and negative charges. We set distances, momenta, formulate molecular Hamiltonian, and then we making an effort to separate variables in molecular Hamiltonian. So first we take the, someone is typing. I see just a little message and I'll answer immediately. So we take electronic part of the Hamiltonian, which is here, and find its eigenstates, which were letter 5. And then we are looking for the overall solution of the molecular Hamiltonian, this letter psi, which is a product of electronic wave functions and coefficients, which at the same time serve the role of the nuclear wave functions. Then we did some mathematical steps to practice the orthogonality relationships to remove this electronic wave function. So basically we plugged in this term 4 times into the equation above, and at the end we arrived to the term like that, and it is not yet new. I'll tell you when to start focusing. So we, through orthogonality relation, we did remove electronic wave function phi from terms from the term 4, term 3, and term 2. And for the term 1, we did practice the second derivative of the product because of the definition. And then we were able to remove electronic degrees of freedom from the half of the first term. But there is a still term that keeps memory of electronic degrees of freedom, substantial traces of electronic degree of freedom here. So everywhere except this highlighted term, we do have nuclear wave function multiplied by delta function. And here we have nuclear wave function multiplied by the term which is not delta function, it is not diagonal. And because it is not diagonal, it brings up mixture between different potential energy surfaces, between different potentials. So it means states of the system are not independent from each other. And treating this term is quite complicated on one hand. On another, at low temperatures, at absence of chemical reactions, it is negligible and it is reasonable to drop this term. So I'm going to tell a little bit more how we drop this term, defining when it is important, and then by the end of the meeting we will go over my version of definition of the potential energy surfaces, hoping that your definitions after the weekend will be better. So I was borrowing some ideas from the book written by this gentleman, and I got his acquainted with him because he was a member of my thesis committee one upon a time, so I decided that it's not bad to read his book, and it was useful through the years. So the term that we were dropping. So here I'm just repeating the derivation that we did last time, is applying second derivative, which is nothing but kinetic energy of nucleus, to the product of nuclear and electronic wave function. And when we practice second derivative of the product of the functions, we are getting three types of terms where the term or derivative is applied to nuclear wave function only is a good term, and we will keep it, and the rest include response of electronic system to modification of nuclear position. So about here, I'm going to say one new word, which also I'm not going to be an eye opener. It's quite elementary, and you may expect it from common sense and intuitive expectation. So I should ask you to give examples, but maybe for the sake of time, I'll give them. So when electronic wave function changes, experience changes upon elongation or contraction of the nuclear bonds, when it is important. So it is important for chemical reactions if molecule fragments on several pieces, if the molecule is irradiated by a strong laser, generally anything what is hot, if we melt, for example, the sample, or if there is a thermal degradation. And there is a class of transfer of reactions where there is a electron transfer and cooling related to photovoltaics. Maybe there are, and of course plasma, if one heats it and ionizes it so that material breaks into elementary pieces, then all terms need to be taken into account very carefully. Okay. So here is our first term from molecular Schrödinger equation, where the pure term, second derivative over position of nuclear wave function is kept, and the terms that include derivative over of electronic wave function are assumed to be negligible. Before I go and drop it completely from our consideration, I would like to say a few words about these terms, because right now we do not need them. But later on, at the end of the course, maybe some of you will decide to look for dissipation of heat from photovoltaic cell or chemical reactions, and then these terms could be needed. So here is how we put back all constants. So I stop dropping constants and write it explicitly in the way how it enters molecular Schrödinger equation. So those are two terms that are being dropped. The name for this terms is non-adiabatic couple. In mathematical sense, they are replacing, they are staying at the same place where we used to have delta functions in all other terms. So in other terms, we had delta function of A, B, and then there was summation over A, same as here. Then nuclear wave function chi A, same as here. When, in other terms, we had delta function, which is the identity matrix with ones over main diagonal and zeros away from main diagonal. The application of such construction was snake meeting rabbit. These two terms were dropping, and as a result, we were obtaining wave function with different index. So instead of summation of products, we got only one term. For these two terms, it is not possible because these terms are not diagonal. They are substantially off diagonal. When there are indices A and B are different, these terms are non-zero. So if you decide to keep them. And therefore, these terms act as mixers. So the terms mix states A and B. They prevent us from factorizing electronic and nuclear wave function. Later on, in about 20 minutes, we will define potential energy surface, and we will accept an idea, practical. It's not mathematically proven, but it is practically accepted that if we set system in a certain potential energy surface, it will stay there forever. It will just re-optimize interatomic bonds, but it will stay in the quantum state corresponding to one potential surface. It's widely accepted, and it's the only way for practical computation. But literally, if there is more than one potential energy surface, there is a chance of jumping between them, especially if the system is heat up, if it is photoexcited, if some intense processes are going on, there is a chance of jumps between surfaces. And these non-adiabatic couplings that we will define with letter theta provide rates or intensities of transitions between potential energy surfaces. If this statement sounds strange or unclear, please let me know. Like, will you accept that this definition that non-adiabatic coupling provides transitions between different states? Yes or no? Should I speak more?
I think, sir, can you actually explain more?
Okay, yeah, with pleasure, thank you. So, um, check, check. I promised to give additional comments in slides 43 and 44. Because right now I was trying to appeal to the concept that hasn't been introduced yet. But I'll remember that we need more comments and try to clean up the definition of non-adiabatic couplings. So these two concepts, potential energy surfaces and non-adiabatic couplings, they are interconnected. And to define one, we need another. Okay. So in some sense, the term here, the second line, is more important because it has only first derivative. This one is vanishing almost always, and the term that I didn't cross, it stays more frequently. It stays more frequently. Also, derivative over nuclei can be treated as momentum, as nuclear momentum. And here is simplified definition of non-adiabatic couple. Na here is non-adiabatic rather than not applicable. So we use this Greek theta. It has two indices, and um, it includes response of electronic states A and B onto change of internuclear distance multiplied by momentum of nuclei. And in this simplified definition, one can see the following rational explanation. If momentum is zero, then the overall non-adiabatic term is zero. So if we are at equilibrium at 0 Kelvin, then momentum will be zero and this term should be dropped. Make sense? If you like quantum effects, you know that there is no absolute zero. There is still 0 point energy and zero level oscillations. Therefore, it still has some very small effect even at 0 Kelvin. But right now we can forget about it. So if I come back to the molecular Schrödinger equation, to our terms 4, 3, 2, and 1, this non-adiabatic term will be dropped from now and for the most part of the course. Then all terms here do include delta functions, which means we can remove summation and delta functions, remove summation and delta functions, remove summation and delta functions, and replace index A to index B. Not here. Here it is already dropped. Yeah, 4 terms. So after practicing this linear algebra thing, we are obtaining 4 terms. This one is dropped. This one is here. This one is here. And this one is here. So let me bring your attention that the nuclear wave function is placed out of brackets. So instead of repeating it 1, 2, 3 times before the equal sign, I just put it out of brackets and put all operators that act on nuclear degree of freedom in the brackets. Now I am coming to the second important component of today's meeting, to the definition of potential energy surface. And maybe this last line and my next 20 seconds will be the most important part of today's meeting. And you see the equation is quite simple. So this equation in the bottom is the time-independent Schrödinger equation for nuclear wave function. This wave function, this equation is done after we did practice Born-Oppenheimer approximation. So we did remove non-adiabatic term. So due to this thing, we do not have summation anymore. So in some sense, we have concise, reasonable equation for nuclear wave function. And for one nuclear wave function, we do not have mixing between nuclear wave functions of different indices. The operator here looks the same as typical kinetic energy operator. It will be just second derivative over position. This nuclear interaction is absolutely the same as in classical mechanics. It's just Coulombic term that repel two nucleons. And here we have unknown eigenenergy for overall molecular system. So everything looks comfortable. Everything looks very familiar to classical mechanics, except one additional term. So if we would write down this equation without knowledge of electronic states, we will not have this blue term. But we do know that depending on specific internuclear distances, electronic degrees of freedom come into certain eigenstate with certain energy. And this eigenstate of all nuclear degrees of freedom must be added into the Hamiltonian for nuclear degrees of freedom. Since it doesn't depend on momentum, it depends on the position. We can pair it. We can pair it together with internuclear distance. So, in some sense, in addition to regular potential energy, we have updated, improved potential energy. So I know that the word surface doesn't have anything quantum in it, but in the community, when people add together this electronic and nuclear degrees of freedom, it's mostly frequently used colloquial word potential energy surface. Potential energy surface. So it is response of the total energy of the system or energy of the system in a certain electronic state to change of internuclear distance. I do remember my promise to give more details and return back to the definition. So it will be in few slides. So I want to give an important comment that one may skip. By looking literally onto this equation, one can think that we are dealing only with ground state of the molecule. But it is not correct. Born-Oppenheimer approximation allows to deal with excited molecules as well. The only difference is that if we so it's very ugly here. I need to learn how to do good images. Therefore, I'm asking you to do one slide next after the weekend, so you'll probably create better images. So suppose I do have a ground state. So the potential energy surface as function of distance will be nuclear repulsion plus this E sub B, but B equals to zero, to the ground state. It means the will look, or if you count, we can count ground state from 0 for 1, but it is energy of eigenenergy of electronic ground state, and it does depend on positions of ions. If by some reason, for example by photoexcitation, we promote electronics, we excite electron from ground state to excited, the original internuclear interaction due to Coulomb attraction stays the same. We'll still have V and N. But the second part, this energy sub B, and B will be equal to 1 if we are in like first excited state, will be different. And it is not only a number. This eigenstate, this energy of electronic eigenstate does depend on nuclear position. And it may lead to the fact that equilibrium position will be at different internuclear distance, which means you excite molecule and it changes optimized interatomic distance. So it's most typical effect that happens in most molecules. Another effect could be that suppose we excited further away to E sub B for B equals like 20, as an example. The character of the potential energy surface can change dramatically. For example, instead of conservative returning potential that brings system after elongation back to equilibrium, so instead of conservative type of potential, it can become dissipated. So continuous line where energy gets smaller and smaller as atoms depart from each other. So such potential would correspond to a photo dissociation. You excite optically or thermally, and molecule breaks on pieces spontaneously. So it is possible only due to additional term in the potential energy surface. Additional term that originates from eigenstate of electronic subsystem as function of nuclear distance. I was trying to draw this figure from year to year, but I do not see any progress. It's still ugly from year to year. But the idea is that different potential energies, different equilibrium, and some states may have more than one minima, and some can have dissociated. Now I'm going to return to the question of K. If we accept Born-Oppenheimer approximation, it means we do not have power to describe mechanism of transitions between states, between different potential energy surfaces. In the Born-Oppenheimer approximation, we assume that we can either look for molecular dynamics in ground state, or we set up certain excited state and we look for molecular dynamics in certain excited state. But if we need a complete picture, we need to see chances for transitions. For example, we bring a system in this dissipative surface, but when it comes to the crossing point, it suddenly decides to jump to another surface and return to equilibrium. and then maybe to return to ground state and come to another equilibrium. So if we want to describe transition, jumps between surfaces, between potential energy surface, then we need non-adiabatic coupling. So, and in the other direction, if we neglect non-adiabatic coupling, if we accept Born-Oppenheimer approximation, we forbid transition between potential energy surfaces. I hope very much that I did answer the question of Kea, but please confirm if it makes sense or it needs more explanation.
No, now it's okay. But maybe I need to read again. Then, if I have any question, then I will ask you.
Okay, okay. So why we were considering these things? Very soon in our practical part of the class, we will go to the very common and important procedure, so-called geometry optimization, where we draw a molecule as humans, and even if you have great chemical intuition, still our interatomic distances can be a little bit off, or maybe greatly off. It depends on concepts used to build the molecule. And then we can run procedure that brings interatomic distances to the best possible configuration. So this procedure that we will do during our next lab corresponds to motion along the surface towards equilibrium, towards position over the minimal energy. So bonds are contracted or elongated to come to the optimal distance. Therefore, it is called geometry optimization. So I will bring couple. By now, we are done with major concepts. I will bring a couple of auxiliary concepts that are of lesser importance. But in case you are meticulous and you want additional information, it's better I quickly glance through them. And we will be done by 10 for sure. So the time independent Schrödinger equation is always good. But if we are speaking about nuclides, we may think out of box. I'm going to bring all of us to the following two-step chain. So time independent Schrödinger equation, then time dependent Schrödinger equation, and then not nuclear, Newton equation of motion. So modern science started with Newton, but we returned back to Newtonian equation of motion, which I believe you already practice when doing molecular dynamics and molecular mechanics, are known to us from childhood. But now we need to look on the Newtonian equation of motion that govern interatomic distances from different angles. Before, we thought that forces between nuclei are controlled only by Coulomb attraction or repulsion of particles. There are some force fields that are tabulated. Now we see additional reason through this electronic potential energy addition. We see the reason why nuclei act this or other way. We need to convert this correct but not useful form into more useful Newtonian form. And since Newton's equation of motion deal with time dependence, right? We need to make a bridge from time independent to time dependent and to Newtonian equation of motion. So this limiting transition. I promised to complete it within 9 minutes. So the line below is, of course, as I always do, ugly handwriting of the time-dependent Schrödinger equation for nuclear wave function. So in addition to dependence on internuclear distances, we make it time-dependent. The Hamiltonian that we used here is will be symbolized by letter H. You can design maybe a subscript nuclear if you want to. And here we do have time dependence. So in the time independent version, we have Hamiltonian action wave function equals energy times wave function. In the time dependent, we do have derivative over time operator. So this equation shows how wave function evolves forward in time if you solve it. And it is very, very typical and useful way to think about solutions, even if we didn't found them yet, as so-called wave packets. So if we know that, and let me focus your attention only on this axis. So we can think of nuclear wave function as distribution, which has some oscillations as wave functions do, but it is centered for most probable or near most probable interatomic distance. Since nuclei are heavy, it is quite improbable that one atom in the molecule will be found very, very far away. Typically, even if they perform quantum properties, they do this probability distribution quite near their equilibrium position. So the width of such distribution, width of the nuclear wave function is typically small. And therefore, there is another approximation. One considers nuclear wave function as very narrow distribution near equilibrium position that can be approximately represented as approximately equals as Dirac delta function, which means infinitely high peak at the point where interatomic distance approximately equals to expectation value of interatomic distance, where expectation value is computed in a quantum way. According to quantum procedure. So this transition from time independent to time dependent, and then to Gaussian wave function for the with very narrow width paves a way from the quantum world to classical world. So if we perform this transition from, if we assume that nuclear wave function is a very narrow peak near the equilibrium position, then through some additional mathematical steps, the time-dependent Schrödinger equation converts into Newton equation of motion for expectation value of the position of a nucleus. Do I have a slide for it? No. Okay, then I think it is where my slides ends and time ends. So I will briefly overview it once again, but I think the lecture was chopped previous year because of it's time to stop. The thing we will start consideration when we meet after the weekend will be returning back to this transition from nuclear wave function to Newtonian equation of motion for expectation value of position. If you are enthusiast of a quantum mechanics, if you were taking several courses, this is related to Ehrenfest theorem. If it tells you something, if you're curious, you can look on it. So for expectation values of the position of momentum, one can use the equations of motion that look the same way as they are in the classical mechanics. With this, I would like to complete today's meeting. Thank you for joining the meeting. Thank you for your understanding and agreeing to, or at least not expressing the protest against this little homework towards Tuesday. And I see some votes, so I'll look through them during the weekend, send you questions if some aspects are missed. And on Tuesday, I will present final version of the schedule that we will present when it will be time for it. So meeting is done. Many thanks. Everyone is welcome to disconnect. And I'll stay here a couple of minutes just to answer questions if any. Boston, would you please send me a brief email with name of the semiconductor that you are studying? I want to prepare for your project and be aware what you are doing.
Okay, will do.
Thank you.
Have a good weekend.
Oh, you too. Have a nice weekend to everyone.
Excuse me, Professor, for the presentation, how long should it take?
As quick as possible. Like 5 minutes would be perfect. Okay. So do not worry about being too short. I mostly worry about you guys being too long because responsible, intelligent people sometimes come into enthusiasm and try to speak longer and longer. So the first feeling is, oh, I'm so, I have a fear. I do not want to say, but as soon as you start preparing, you will have wish to speak for like half an hour. So try to be condensed, to have maybe 4 slides.
Okay.
Please your story into 4 slides.
Thank you. Have a nice weekend. Take care. Goodbye.
Goodbye.
So, can I ask Dr. Cullen?
Yes, yes, Lina.
So, it's tentative topics for 3-minute presentations and then computational chemistry in 30 minutes. So, what's the official time for the presentation again?
It will be during the lecture.
Okay.
I suggest that we do it next Friday at this time.
Okay.
If someone will vote for something different, I'm open, but it seems reasonable because
Yeah.
so total we have about 12 labs. So after 3 labs, we summarize what has been done.